So, over the next 2 weeks, basically, this week and next week, oh, this is chapter 7 now. This drives me nuts. So our new book, like, has a chapter that our old book didn't, and so everything got, like, bumped after chapter 6.
I feel like those people do it on purpose.
Okay. So anyway, this week, bless you, and next week will be dedicated to finding different volumes. Okay. So what we're going to do today and tomorrow, we're going to work on volumes of rotation, and we'll do that next week too with a different method. But basically, we are going to take an area, and we're going to rotate it around an axis to get a three-dimensional solid, and we're going to find that volume. Okay? So, first of all, this looks like something that you would be able to find the area of, correct? Okay, so what we're doing is we're taking that bounded area and we're rotating it about an axis, and we're going to find the volume. Okay? Now, by the end of this, we're going to be able to find it 2 different ways. Today and tomorrow, we're going to focus on the disc washer method. Okay? Why is it called the disc washer method? Okay, so what I want you to do is, I'm going to go through some slides with some animations. You won't need to write everything down. I'll tell you what needs to be important.
What about like a stadium, like it keeps like adding it, like kind of slowly, like it keeps going around? I think I saw the one Griebel slide flash when he was working on it.
Yeah. Yes.
Just out of curiosity, I noticed it says dx and dy. Since we're working three dimensions, does that mean we're also going to be working with dz?
No. No. That would be if we were in a three-dimensional space. We're still in the 2D plane. We're taking a 2-dimensional area in our plane and we're rotating it. Okay. So, what we're going to do is we're going to take a region, okay, bounded on top, f of x, and bottom, g of x, from A to B. And what we're going to do is we're going to rotate it about an axis. And we'll start today with just rotating around the x-axis, and then we'll eventually be able to rotate around different lines, different horizontal lines. Okay, but we're going to take an area, and we're going to slowly but surely rotate it around to get a solid. Okay, kind of cool, right? Okay. Okay, so how are we going to figure out the volume? We are going to take this bounded region and we're going to break it up into infinitely many rectangles. Sound familiar? Okay, okay. So it's probably going to deal with an integral, isn't it? Okay. So we're going to have little rectangles. What's our thickness?
Yeah, infinitesimally small.
Okay. When we rotate these, we're going to get discs or washers. Okay? If there's space in between our region and the x-axis, we're going to get more of a washer than we are a disc. Okay, do you see how that's going to work? Okay. I meant to bring it today, forgot, so I'll try to bring it tomorrow. But you know that toy that you play with when you're your baby where you stack the rings? Okay, that's kind of what this is going to look like. All right? I'll bring it tomorrow. So, what we need to be able to do is find the volume of each of these infinitesimally small washers. Okay? So my first question to you, how do you find the volume of a disk? Pi r squared times pi. Excellent. How are we going to find the volume of a washer?
Minus.
What's the distance between our?
It'd be
have a radius.
It'd be big disk minus little disk.
Okay, big disk minus the little disk, right? So let's write that out. let's draw a picture here. So we want that red minus the purple, right? Because we want to take out that hole, okay? So we want pi r squared h of the outer disk minus pi r squared h of the inner disk. This is an important thing for you to maybe jot down. And so what we're really dealing with is pi times r squared minus r squared times h, if you factor out the pi and the h. Okay, I still kept it in the pi r squared h order. Okay.
It's like H. R squared H.
Right. But pi r squared h is the order we like to say it, right? Okay. So now let's go. Yes. Hold on. Oh, did it stop going through? That's a disc. That's a washer. A washer has a hole. Have you ever seen a washer like the game? Well, they're actually for like things that you make, but it's like a flat donut because there's a hole in it. There are these little metal
Why
things.
don't we
that
just
you-
call it the donut?
What's a sphere?
Because
Why
it's
do we
not
call it
some-
the disc and donut?
Because if you think about a washer, it's like really thin,
Mhm.
and that's what we want to make.
No, we want to do
Okay. Scott, do you have a question?
jelly filled and non jelly.
Okay, so now let's go back to what Nathan said earlier. Oh, we're probably gonna have to use an integral, right? So let's go back to our picture, okay? So our radii, that's plural for radius. Our radii, okay? If you think about it, this top function back to the x-axis, that's our outer radius, right? For our washer, and then our bottom function to the x-axis, that's where that hole is, so that's going to be considered our inner radius. So we can go ahead and change this to our radii become our functions, okay? We still have top minus bottom though, okay? Because we want our bigger radius to be first and our smaller radius to be what we're subtracting. And then if we think about the thickness is what we consider the height of these discs, pi r squared h. Well, that height is that very small thickness is what we like to think of it. Okay, we've been labeling it dx, right? So there we go. Okay, now we have an infinite number of these very small washers that we have to add up. So we're going to have to take the sum of all of these washers as the thickness, as the limit approaches infinity, right? Which means, what are we talking about? We're talking about an integral, okay?
Riemann sums.
We know what Riemann sums give us, right? So this is what's important. Ta-da!
Oh my gosh.
It's okay, you can write it down. You can write it down. But I just wanted to give you the ta-da, as we had like that anticipation building.
Really?
We did.
She's gonna feel it?
I think that's just the pain.
Yeah.
Do you have a headache, Jimmy? I'm sorry.
Are you?
Is math giving you a headache?
Just got done.
Okay, so can I go to the next slide? Ta-da! So pi r squared h. Okay, and what will A and B represent? Where we begin and end. Potentially what they tell you, or our intersection points of the two, intersection points of our region. Are you okay?
Why are you looking at me? I didn't do anything.
I'm just making sure you're like having your tummy like.
Oh, me.
Oh,
Do you go back?
no,
The right. Okay. What am I gonna make you do every single time you have a problem? You better have a picture and you better have a reference rectangle, and you better have a vision of what we're rotating. I'm not gonna make you draw a wash. Okay, y equals x. Okay, first of all, what's x equals 0? What is x equals 0?
Y-axis.
Okay. Y equals x. Y equals x minus 1 squared plus 1. So that's a parabola shifted up 1 and right 1. Like that, right? Does this part matter? Nope. Okay. Okay, I'm just going to clean up the picture a little bit so it doesn't get too busy. Okay, and what are we going to do with this region? We're going to rotate it about the x-axis.
How do you afford to cut it?
That's where all three of those lines or those curves intersected, because we had x equals 0, y equals x, and then our parabola. So where all three of those intersected together, that's the region that we wanted. Okay? We are going to rotate this about the x-axis. So what's going to happen is we're going to get something that looks like that. That didn't go very well for me. Yeah, I did.
What?
What?
How are you supposed to draw that?
I don't.
Oh, we're scared. It's just a reflection.
What do you do? Just flip it and then make a
Yes.
circle?
Now, it's not a fabulous picture, but what I have to have is that blue, this little twisty guy, and a reference rectangle.
Does it matter which direction you draw the arrow?
It just has to rotate about the x-axis.
Looks like the volcano.
Okay?
You should draw.
All right. So notice when we draw our reference rectangle, we have thickness dx. Okay? Eventually, we're going to learn a second method, so this is so important that you draw that reference rectangle. Okay? Let's talk about how we set up our integral. So we have pi r squared h. Do not forget that pi. All right. Where is our integral going to go from? What are our limits of integration?
To 1.
Okay, we begin at 0 and we intersect at 1. So from 0 to 1. Okay.
Wait,
Oh, okay.
Okay. So our top function is our outer radius. So our top function is x minus 1 squared plus 1. That's our top function squared, pi r squared, minus our bottom function is y equals x. So there's our inner radius squared. So we have pi r squared h.
And we just punch that into our calculator.
Yes, now, get out your calculator so we can practice this. Are you going to put the pi in right now?
No.
I would not, because I'm going to want an answer that's like 9 pi over 2, or whatever. I don't know the answer to this is. But I want your answer in terms of pi right now. Okay? So go ahead and punch it in, and then we'll worry about the pi. All right, Kristen, something came up on your calculator. Where'd you get?
23, 15, so 23, 5, 15.
I got 1 point.
I got 1 over 5.
I just got one.
Yeah.
Well, change it to a fraction.
I got 23, 15 over 5.
You did not square this guy.
Dude, I got the same meeting. Oh my god.
Do we all know how to go from a decimal to a fraction?
Yes, math and turn. Oh.
I got negative two.
So it's basically the same thing, except you're multiplying it by pi and square. It's very similar. in this way.
Well, we're going with the same system of top minus bottom, right?
Oh, so that's still right.
Well, because this is, right, this is our top function squared
So no,
minus bottom function squared.
so it's still top minus bottom.
What will that help?
Because otherwise it's just, I'm gonna have to rethink the whole thing again and see how it makes sense. And I'm just gonna have to prove it again, and prove it again, and prove it again, and prove it again. Okay.
Was everyone getting that? Oh, no. Oh, good.
Oh,
Is
no.
everyone getting that okay?
So did you do the math?
Is that it?
And you multiplied by pi?
Yes. Yes. Now, there are going to be times where you don't get a fraction and you're going to have to multiply it by pi and give me a decimal. But for the most part, I want you to try and get a number in terms of pi.
Is that it then? That's your answer?
Yeah. Okay. Example number 2. Of course, there's more.
Let's start with that then.
46.
We have this example and then 2 additional. So 4 examples. That way you feel good about starting your homework. Okay. This is a nice graph, isn't it?
Hey, sorry.
Wait, for the disk thing, would it be, would it pretty much be, just the original plate, just the same thing except the second came out, anyway, this is just 0 for this?
For, yeah. And that's what this example is going to let us know. Okay, so this is the area that we're working with. Do you agree? So they gave us a curve, and they said from 0 to 4. So here's from 0 to 4. What we're going to do...
It says 1 to 4.
1 to 4.
Oh, dang it. It says 1 to 4. So what we're going to do is we're going to rotate this about the x-axis, and we're basically going to get like a, you know what, kind of like a trophy?
Oh,
Or kind of like a,
A bowl with a hole.
okay, a bowl.
yeah.
Like a bucket.
So flat here, right? I would not say that there's a hole though. Why is there not a hole?
Because it's all indicates.
They're all discs.
Okay, our area goes from our curve all the way to the x-axis. So when we draw in our reference rectangle, the x-axis is our bottom function. Okay. So when we set up our integral, pi r squared h, okay, they already told us we need to go from 1 to 4. Our top function, okay, is the square root of x. So we have the square root of x squared.
Which is just the X.
So it's just X.
Yes.
Oh.
Minus our bottom function is the x-axis. You can write 0 squared. There's nothing wrong with it, but you don't need to. So basically what we have is this. Okay? This is one that is doable by hand. Do not type that into your calculator. We are going to do it by hand.
That's 4 minus 1.
All right, John, what is the antiderivative of x?
So it was like, 1/2 x true.
Okay. So we have pi. I would just leave your pi on the outside, wait for it until the very end. So when we plug in 4, 1/2 times 4 squared
16.
8.
minus 1/2 times 1 squared.
1/2.
8 minus 1/2,
7/8.
7 and 1/2.
So 15 halves, so we're gonna say 15 pi over,
Hey.
Is this exact color we have our desk?
probably not. Okay, so we feel pretty good right now about rotating around the x-axis.
And I'm gonna make you feel like
wait,
that.
there's
This
more.
next problem.
You're the one.
That's smart.
Crap.
Now we're gonna rotate about
6,000.
I'm out of line. The negative line.
different horizontal lines,
Oh.
okay?
Is that what
So-
trans?
Transition. So we have two curves, y equals x squared and y equals x. And now we're gonna rotate it about the line y equals 2. So y equals x is a line. Y equals x squared is a parabola. What are we working with? This little teardrop, right? What are the intersection points? We don't need to think too hard.
1, 0.
1 and 0. Okay. So y equals 2 is the line that we want to rotate it about. Okay. So we're still rotating about a horizontal line. It's just not y equals 0. It's not the x-axis. So what we're going to do is we're going to take these little reference rectangles. So can you imagine, like, ugh, it is an ugly shape, okay? So we have this teardrop that's twisting around. And what I want you to imagine with me real quickly is that little rectangle being rotated about. Can you imagine how those are going to look like discs? How small they're going to be, but they're going to be little skinny rectangles rotated about. Okay? So now, okay. We are still going to have pi r squared h. And we'll go ahead and fill, this is going to be from 0 to 1. Now, when we have a line that isn't the axis, we're going to have to take that into account. So if you think about it, where is our longest radius? Okay? From here all the way to here, right?
Yeah, what?
Okay, so think about these discs. We have a radius from here to here, and we have a radius from here to here. We have to go from the axis of rotation to each of our top and bottom of our rectangle, right? So we're still going to do top minus bottom, but we have to do big radius minus small radius, right? So our big radius is going to be this function 2 minus this function. So 2 minus x squared, that's our big radius. This is y equals 2. And we have to go all the way to our biggest radius, so all the way down to the bottom of the rectangle. Since we're above, our biggest radius is going to go to the bottom of the rectangle. Minus inner radius squared. Well, from our axis of rotation, our smallest radius would be from the axis to the top. So 2 minus x, quantity squared.
So now we're doing bottom minus top.
Well, let's still think of it as top minus bottom, because we're taking that y equals 2 minus a bottom function, right? But we just have to do big minus small. Otherwise, we're going to get a negative area.
So is there any case where you'll have like the big radius will be top part.
If our line is underneath.
So if you just rotated that like a month, two.
So like if we rotated about y equals -2, then we'd have to do function minus the line. Okay?
And why are we doing it on this problem with the washer? How do we fix the washer?
Okay, I want you, well, a washer and a disc is a washer without a hole.
How do we know about the whole?
If there's a space between your function and the axis of rotation, you're gonna have a hole. Like here, there was no space, there wasn't a hole. Here, there was a space, so we had a hole. You see what I mean there?
It's like that ice
So we like need and like know
like a piece of string.
As long as it, you don't necessarily need to know that because your hole may just be 0, right? Like it was in our last example. Okay? Is everyone okay with this setup?
And, why is it 2 minus, shouldn't it be minus?
Top minus bottom.
Because we still have to do top minus bottom.
Yeah.
So top function minus bottom function. Top function minus bottom function.
Oh, so you're using y equals 2 as top function?
Yes.
Okay.
Yes. Okay.
Then-
Now, okay, other questions? Go and plug it into your calculator without the pi.
8,015.
Oh, you already did? If you had to do this one by hand, you'd have to FOIL those out, combine like terms, and then do it by hand.
Great.
So glad.
Is that what you're at?
Okay, so you can imagine that not all of these are going to be convenient without a calculator, right? Yeah.
So if the like line we were like rotating about with like and we put like x squared minus like
Okay, do you want to use the same example to rotate about a different line? Or do you want to do a different example about a different line?
Different example, but different.
Excellent.
That's just-
Because I'm using PowerPoint instead of Smart Notebook. Yes. No, what? This is not a real PowerPoint.
This is
I do my
agreeable.
own.
It's agreeable.
Kinda looks like
This is agreeable.
We've been doing. Yours are integrables. We've been doing integrables.
I do my own notes and we collaborate on our worksheets.
So it's great when just talking fast, so you want to, is that how he does it? Cause I know people.
You work together. You guys are just bossing me around.
What is Greenville?
It's great. Well, that makes sense.
I take offense to that.
How? I'm saying.
You're telling me that I don't do any work.
No, I'm not. Well, you do, you easily do plenty of, you do too much work.
Okay, thanks.
Mr. Grable and I collaborate on all of our worksheets and quizzes and tests.
You guys think?
The dream.
That dynamic duo.
Last example.
It's almost like Russell Westbrook and Bruce like
We're more of like the Scottie Pippen, Michael Jordan era.
Are you
Who's
picking
Michael
them?
Jordan?
Who gets all?
Oh, who's the Jordan?
Who's the goat?
Like the guy who's working for him.
Is that what you're calling Scottie Pippen? Go.
No.
MJ's the
Yeah,
good.
Mango. Kratos.
Scottie Pippen had all the assists.
That isn't.
Okay, so we have 1/2 x squared, x equals 0, and y equals 4. Yep. Where do those intersect at? Where do they intersect at?
Zero and
I said,
Square root of 8. Plus or minus x square root of 8. No, it's positive. It shows right here, it's positive.
yeah.
But it says plus or minus.
Because over here, it would also intersect, right?
yeah, so how do you, so you just don't worry about that region of there? Oh my gosh, man.
Well, because it says x equals 0. Oh,
It says at the top.
it says x equals 0, which is this, y equals 4, and the parabola. So yes, there's still parabola over here, but this x equals 0 is cutting it off.
That doesn't
So
make
how do
any
you know
sense.
which side to choose?
Yeah.
Okay, so I need to
Because it's
reword
like
this.
x
We're going to
equals
go
0.
with with quadrant 1. Okay, so now we want to rotate this about the line y equals -2.
I wish.
Okay, so we're still going to do pi r squared h here. Our limits of integration 0 to square root of 8. Okay, our outer radius. If you imagine these little rectangles twisting around to make a washer, where's the biggest radius? From here, furthest away from the axis of rotation. That's a good way to put it. Thank you. Okay, the furthest away from the axis of rotation. So what is this top function? Y equals 4 minus minus -2. So there's our outer radius minus our inner radius. So that's going to be the closest to our axis of rotation. So 1/2 x squared minus -2 squared.
So like the other problem, our y minus, our y equals 2 was our top, then now it's our bottom.
Because it's below. Okay? You still have to do the top minus bottom, top minus bottom, top minus bottom. You just have to think about where your line of rotation is, where your axis of rotation is. So your homework is on page 453. You have 1 through 6. 11 only A and D. B and C will come tomorrow.
What's A/D?
That means only do A and D.
Yeah, what's up?
I didn't even write down my final answer.
Oh,
208 pi?
Oh. Yeah, so 208, Zach.
285.
Okay.
208. 66 pi or.
Yeah, I think that's it. All right, so these are the ones I want you to do by hand.
What's the final answer?
I'm sad I didn't get a place.
Well, we have to do anything.
Oh, yeah. Essentially,
Why you?
I want you to do 1 and 5 by hand.
Wait, 1 and 5?
Sure. Yep.
Yes, straight up like a little.
Some dude just walked in there. Thanks, you look Instead of walking back, you know, it's gonna walk in the phone. You're escaping from this job. Okay,
Follow bouncing the great weekend, like all right, the
He was dancing.